Hi, welcome back. In today's video, we're going to talk about tangents and how they relate to circles. We've spoken about tangent before in terms of SOHCAHTOA. Now we're going to talk about tangents in a very similar form, but now with circles. I'll do my very best in this video to not go off on a tangent, don't worry. Joking aside, tangent is very much like when you have a conversation and you go off on a tangent. Usually in that conversation, you are talking about a particular topic, and then there's a particular point in that conversation where you go off topic. So like point A in this circle, circle C, would be our point of tangency, because point A, that would be the point in the conversation where you go off to a completely different topic. So we would say line AB is tangent to circle C. And what it means by it being tangent, it means that it only shares one point in common as that circle. And that's what we call the point of tangency. This point, point A, is the only location on the circle and on the line that they both share in common. More specifically, the point of tangency will intersect the circle with the radius, or diameter if you want to extend this. It'll form a 90-degree angle. So a line that is tangent to the circle will always intersect at 90 degrees. This is also part of the reason why SOHCAHTOA, when we use the function tangent, it only worked for right angles. But that's a conversation for later. The key thing here is that if it's tangent, it'll form a 90-degree angle with the radius. So as you can see below in this first example, we want to figure out whether or not this triangle is a right triangle. Do we know if KL is tangent to the circle? Meaning, at this point, does it form a right angle? And the way to find that out, right, as we discussed before in our previous units, we spoke about when we're given three side lengths of a triangle, we can determine whether it's a right triangle, an acute, or an obtuse based on whether or not it fits the qualifications of Pythagorean theorem. The Pythagorean theorem that we've been using only works, it only equals c squared when it's a right triangle. So since we have a triangle here, we can determine whether the side lengths actually create a right triangle by checking the Pythagorean theorem. This length right here is 9, and we know since the radius here is 8, this section here, I'll do it in a different color so you can see it. This section of the circle would also be 8. So if we're trying to do Pythagorean theorem, you can see how we have the full hypotenuse is 17. And then we have side lengths 8 and side lengths 15. So when you plug it into the formula of Pythagorean theorem, we have 15 squared plus 8 squared. And we want to know, does this equal 17 squared? I got 17 from this full length. I took the radius, which is in red, and the outside part of the triangle. So let's do some math. 15 squared is 225. 8 squared is 64. We want to know, does it equal 17 squared, which is 289. When we add 225 and 64, we get 289. So it actually does equal 289. Since these dimensions, 8, 15, and 17, actually work for the Pythagorean theorem, we know that we're dealing with a right triangle. Therefore, we know that this line, KL, intersects at 90 degrees. Therefore, it is tangent. Line KL is tangent. Had this equation not worked for us, it would have not formed 90-degree angle. It would have formed something completely different. So now let's say that we know the fact that we have what we know about tangents. Can we use tangent lines to find missing values of our circle? Since this is a tangent line, BC is tangent, we know that it will form a right angle. So anything with right triangles and lengths, we can use Pythagorean theorem. If we knew an angle, we could use SOHCAHTOA, but we don't really know the angles. All we know here for the right triangle is that we have the side lengths of a right triangle. So let's do Pythagorean theorem. We have a squared plus b squared equals c squared. We can label this side to be a, this side to be b, and this full length to be c. So we have x squared plus 12 squared, and that should equal, sorry about that, that should equal the length of c. Now this full distance, this hypotenuse, is the sum of those two parts, x plus 6. We're going to square that because it's a squared plus b squared equals c squared. We do a little bit of math here. We have x squared plus 144, and this equals x plus 6 squared is really just x plus 6 and x plus 6, right? It's x plus 6 times itself, which means I have to do a little bit of FOIL or a little bit of a box method, depending on what you're comfortable with. So here's a bit of a review from Algebra 2. We can do FOIL. We can say this is x times x is x squared. X times 6 is positive 6x. 6 times x is positive 6x. And 6 times 6 is positive 36. All of that equals x squared plus 144. This is really just an Algebra 2 problem. At this point, we want to combine like terms. I'm going to continue solving this up here. X squared plus 144 equals x squared plus, I'm going to just combine these two so they're on the same side, plus 12x plus 36. I'm going to move this x squared to the other side, so I subtract x squared on both sides. Notice how those get canceled. And since I'm left with just an x variable, I'm going to want to move this 36 to the other side. So I have 144 equals 12x plus 36. When I isolate the variable, I move the 36 over. 12x equals 144 minus 36 gives me 108. I divide both by 12 because that's the inverse of multiplication, and I get x equals 9. Here, because I was told that BC was tangent, I could use the fact that it's a right triangle, and I use Pythagorean theorem to solve for the value of x. Now from here, can I determine the length of the radius? Absolutely. When I plug that in here, the radius of this circle, here or here, the radius will be 9. Feel free to pause it, slow this down, go back a little bit if you need to, and do this problem again. Another property of tangents is that whenever you have two tangent lines, so we know that we have a tangent line over here, tangent to the circle, so it technically forms a right angle. I have another tangent line over here, which means it'll also form a right angle. When they share the same point here on the outside, what this theorem says is that the lengths of these two tangent lines are going to be congruent. The length of BC will be equal to the length of BD. They are congruent. So, as you can see in the example below, we have two lines that are tangent. I want to solve for the value of x. So I know that our equation here is going to be the same length as this other equation. So same means equals. I have 2x squared plus 7x minus 5. That line has to be the same length as x squared plus 3x plus 7. They are the same length to each other. I want to combine like terms, and I move everything to one side. So I subtract the x squared over here, so I can combine the x squares. 2x squared minus 1x squared is just x squared. I want to move the 3x over, so since it's positive, I do minus 3x. I have x squared plus 4x minus 5. 7 minus 3 is 4. and that equals 7. When I move the 7 over, subtract 7, I have x squared plus 4x minus 12 equals 0. And as we've been doing all year, when we solve a quadratic, you have to factor this, right? You have the two options that we've spoken about, where you can do your columns, find the factors, cross multiply, right? But hopefully by now, we feel comfortable. I mean, if you have to do this, go for it. X times x gives me x squared. And then I know 3 times 4 gives me 12. And 2 times 6 gives me 12. But the one that adds into or subtracts to 4x in the middle is going to be 2 times 6. If you prefer the ACB method, go for it and do that. Whatever works for you. I know it's 2 times 6. When I cross multiply, 6 times x turns into 6x. 2 times x gives me 2x. These two values had to add up to a positive 4x. And the only way that it's going to add up to 4x is if I make this a minus 2, which means this should have been a minus 2. And hopefully that works for you, right? That makes sense, because a negative 2 times a positive 6 gives you a negative 12. And at the same time, 6x minus 2x gives you a positive 4x. Anyway, here we have our factors. The values on the outside are our factors. X minus 2 and x positive 6. They both have to equal to 0. Now I can solve them separately. You set x minus 2 equals 0 and x plus 6 equals 0. Move the 2 over. X is positive 2. Move the 6 over. X equals negative 6. Now here we're solving for x, so we're pretty much done. But whenever you're solving for a value, notice how we get two possibilities. You always want to make sure that the possibilities are actually true, that they work. So what do? We can take our answer, and you're going to want to plug it into the length. When you plug the value in, you're going to get a particular length, right? So if we plug 2 over here, we're going to have 2 squared plus 3 times 2 plus 7. 2 squared is 4. 3 times 2 is 6 plus 7. So when you add all of these up, 4 plus 6 plus 7 is just 17. The length of BD is a positive number. So I know I'm going to keep this as a solution. I can do the same thing with the negative 6. Plug the negative 6 in here and see if I get a scenario that actually works. Remember, we cannot have negative lengths. So let's plug in the value inside and see if we get a negative length. So we got negative 6 squared plus 3 times negative 6 plus 7. Negative 6 times negative 6 is positive 36. 3 times negative 6 is negative 18 plus 7. When you add these values up, 36 minus 18 plus 7, we end up getting positive 25. Notice how both of them resulted in a positive length, which means they're both solutions here. X is going to work and negative 6 are both going to work as a potential length of this tangent line. I know this looks like a lot of problem or a lot of work, but the most important component here when we're dealing with these tangents is really this first step. The key part is this. The two lines are equal. That's it. If you have a linear scenario, make them equal to each other. If you have a square root scenario, make them equal to each other. And in this scenario, we have quadratics, make them equal to each other. This is really what the geometry component is about. Everything after that, all of this work that we've been doing, has been just algebra 2 work. This is our geometry component. The geometry says that the two lines are equal. Do that and then solve whatever it takes. Wherever it takes you, just solve that problem. So here we have a circumscribed polygon. So if we review back to 10.1, parts, definitions of circles, when a polygon is circumscribed, it means that the polygon right, will fit perfectly inside the other. We have this circle that is circumscribed, right? And we have this polygon that goes around it. Now, because it only crosses at one point, we know, I'm going to do this by three different colors, we know that these two lines are tangent, which means that these two blue lines are equal, right? That means that this is also 8. On the other side over here, I have these two lines are also tangent, which means these are also congruent to each other. So FB is also 7. If the full length is 10, we know by default, I'll do a different color. Let's see. We'll do it in pink. I know by default that what's left over is 3. This length is 3. And since these both are tangent, that means that they're both equal to 3. And what this question is asking for, now that we have found all the missing sides, is can we find the perimeter of the triangle? The triangle that is circumscribed about the circle. I have all the lengths. I can just add them all up. I have 8 plus 8 plus 7 plus 7 plus 3 plus 3. And when you add them all up, you end up getting 16 plus 14 plus 6. That's going to give us a total of 36. Is the perimeter of this. The thing that we needed to know is that the lines, when it circumscribes a polygon, the lines are tangent, so you have a lot of lines that are equal to each other. Okay, so we've reached the last part of our set of notes. Here we have additional practice problems. Like in the other videos, this is a good point for you to do some individual practice by yourself, right? Some individual practice, just you. Press pause, try these 3 scenarios out, and see if what we just covered, or see if you learned what we just covered. See how much stuck to you, okay? Feel free to press pause, try the problem, and then press play and see if you get the same answer that I do. For this first scenario, we're trying to identify whether or not GH is tangent. Is this line intersecting at 90 degrees with the radius? Right? So the way to do that is, again, Pythagorean theorem is the only theorem, right, that works with side lengths of a right triangle. So I want to know, does this work? I have A, I have B, and I have this full length as C. Since the radius here is also 6, the full length is going to be 18. So let's try Pythagorean theorem. I have 8 squared plus 6 squared should equal the hypotenuse, which is 12 plus 6, 18 squared. 8 squared is 64. 6 squared is 36. And 18 squared is 324. Does the left equal the right? Does this actually work? 64 plus 36 gives us 100, and that does not equal 324, which means this is not going to create not a right angle. So since it does not form a right angle, this picture wasn't drawn correctly, which would imply that the line is not tangent to circle F. Tangent means that the line HG, let's make it a different color, the line HG will only meet at the right degree angle. So since the Pythagorean theorem doesn't work, it does not form a right angle, which means it is not tangent. GH is not tangent to circle F. Next example. Find the value of x. Assume that the segments that appear to be tangent are tangent. So we're going to assume that this line is tangent to the circle this line is also tangent to the circle, and this line is tangent to the circle. What does that mean? It means that all of these lengths are going to be congruent. From here to here is the same length as this, and it's going to be the same length as this. All these three lines on the outside that meet in the same place are the same length. So since they're all equal, I can set 3x minus 8 equal to x plus 10. The length 3x minus 8 must be the same as x plus 10. And I just solve for x. I move this x to the other side so that I can combine like terms. I isolate the variable by moving the 8 over. 2x equals 18. Divide both by 2, and you get x equals 9. When two or more lines that are tangent intersect at the same point, they become congruent. So this is going to be the same as this and as that. Let's try our last scenario. We're trying to figure out the value of x, given that this quadrilateral is circumscribed about the circle J. We know that the total perimeter is 18. Right? So all of these side lengths around are going to add up to 18 as our perimeter. Since these two are tangent and they meet on the same line, they're both going to be equal to x. Since these two are tangent and they meet at the same point, we call that also x. Since these two on the bottom right are tangent, they're both going to equal 3. And then the same thing on the other side. The both on the left are going to equal 3. So I add them all up. I have x plus x plus x plus x. I have 4 x's, right? Plus 3 plus 3 plus 3 plus 3. I know that all of them are going to add up to a perimeter of 18 units. So x plus x plus x plus x gives me 4x. 3 plus 3 plus 3 plus 3 plus 3 gives me 12. And that should be 18 total. Subtract 12 on both sides. 4x is going to equal to 6. Divide both sides by 4. And x equals 3 halves, or 1.5. And that's it. I hope this has helped. Please let us know if you have any questions. Don't forget to like the video, subscribe if you haven't already, and as always, we'll calculate later.